Okay, so I'm just moving this chair out of the way. I've stuck this diagram on the wall, so I can't really get to it very easily. Just move this out of the way. Oh, right. So yesterday I was talking about a problem. The solid state relay circuit, once it's energized and it's connecting these batteries together, so let us say that's channel 1, that's channel 2, and that's channel 3, channel 4, channel 5, channel 6. Now, we're disengaging the solid state relay. The connections, if there's a load, even a slight load, just the slightest little trickle of current going through it, will keep the solid state relay active so that it's still connected, right? So I was talking about pulse DC, actually pulsing the DC, so that the DC is on, off, right? In that situation, these connections would disconnect even after the solid state relay being de-energized, as in the trigger circuit was disengaged. The only problem is if there's the slightest imbalance between these cells here. Let's say this battery had more power in it than this battery, and this battery had more power in it than that battery, right? What would happen is there would be a current flow. Basically, this battery would want to equalize itself. Power would want to shunt from that one to this battery to equalize this battery that's lowest. So the problem with that is that the solid state relay would remain energized even when it was not active, right? You would have to interrupt the power supply between these two batteries to break the connection so that the solid state relay would go open, right? So I'm thinking about this, and I came to a conclusion that instead of using 1, 2, 3, 4 channels for these batteries in parallel, we would need to use 5 channels so that the solid state relay would basically be connected through a diode. So we'd have a diode connected to this cell, a diode connected to this cell, a diode connected to this cell, so that power during the charge cycle, when these 3 batteries are in parallel being charged, the power could no longer flow from that cell to this cell. It could only flow from the external source. And obviously where that LED is, I would have a full wave bridge rectifier so that when these cells are switched around, this would become positive, this would become negative when the cells are configured differently. So the bridge rectifier would always send out positive and negative, right? So it's like a AC to DC rectifier circuit. Now, if we had diodes connected to all these 3 cells, then we would need 3 channels because we'd have to use the solid state relay to each diode, right? So they'd all have a common. So the common would be connected to this end right here. So the common of 5 of the channels would be connected. No, sorry, the common of 3 of the channels will be connected here, right? So then this would become the common for the positive during the charge cycle of these batteries in parallel, right? So we'd have one channel going in through the diode, another channel going in through the diode, another channel going in through the diode. So these cells could no longer maintain a circuit when they were deactivated. These channels, these connections on the back, the negatives all connected together, that would be fine because the circuit wouldn't be completed because these are going through diodes at this end. So these can still be connected directly across. So the one channel there, so they can be connected through the solid state relay. Yeah, so I did a lot of thinking about this earlier on. Now the other issue is interrupting. How do we interrupt the DC so that we could break this connection? The way to do that would be through the bridge rectifier. We would have, obviously that would be an LED, it would be a bridge rectifier instead. So what we'd do is send that output from the batteries. Obviously the charging circuit would be separate to this, so it would come in through another diode to these cells, obviously, through the another channel of the solid state relay. So the way to do that is the bridge rectifier, which we would have there, would be sending power out through a timer, a 555 timer, which would activate a transistor, which would basically be on, off, on, off, on, off, on, off, say a relatively low frequency, you know, maybe 50 kilohertz or something, or 50 hertz, sorry. And we would send that into a capacitor, which would be charged. You know, so the transistor would charge a capacitor. The capacitor itself would provide the power to run the device, whatever we're running, whether it be the solid state meg or a motor or something else. So the capacitor will be charged through the oscillator circuit of the timer through a transistor. So the capacitor would have almost a constant DC voltage in it, but it would be slightly up and down like that because it'd be getting pulsed, right? So the voltage would be going up and down like this, but it would get a relatively stable DC voltage to whatever load we're running. So anyway, that's my solution. That's what I was thinking about, and I just have to draw that diagram up in my circuit in the DESIGNSPARK circuit diagrams. So I'll probably do a scratch drawing of it first and on a bit of paper. I'll probably just do a basic block diagram to work it all out. So yeah, that's what I need to do next, is a simple block diagram, working all this stuff out. So anyway, that's my solution that I've come up with. Anyway, I hope that clarifies a few issues, and hopefully it should work. Obviously, I'm going to be building this before I actually build this on a circuit board. I'm going to build it on my breadboard, my prototype board. So I would have to strip all this crap off here, all this mess off here, and build a prototype circuit on here on my breadboard. Oh God, it's dusty. I haven't used it. That shows you how long it is since I last used this. So last time I think I was doing that switch and that. Yeah. So anyway, I hope you learned something. Bye for now.